In this video series, we will talk about the chi-square distribution and use that to give a proof of the famous Johnson Lindenstauss lemma, which is a very famous theorem in the theory of dimensionality reduction in data science. To begin with, let us first talk about the definition of the chi-square distribution. The chi-square distribution with k degrees of freedom is a distribution of the sum of the squares of k independent random variables, each following a standard normal distribution. Using mathematical notations, if X is a chi-square distribution with k degrees of freedom, then it can be written as the sum of k RID standard normal random variables. Recall that the probability density function of a standard normal random variable is 1 over square root of 2 pi times e to the negative x squared divided by 2. To study the chi-square distribution, let us begin with the study of the moment generating function of it. This is abbreviated by MGF. Okay. Let X be a random variable following a chi-square distribution with k degrees of freedom. We can write, as I wrote here, X is the sum of xi squares from I equal to 1 to k, where x of i's are independent and following standard normal distribution. And now let's compute its MGF. Recall, the moment generating function is defined as the expectation of the random variable e to the t times this random variable x. This t is a real number, but its range is still to be determined, because maybe for some t, this integral doesn't make sense. So we have to determine the range of t. To compute the moment generating function, we're just gonna plug in the definitions. The moment generating function by definition is the expectation of e raised to the power tx, which is the expectation. Now x is a k degree chi-square distribution. So we write it as the sum of xi squared from I equal to 1 to k. And now, because of the property of the exponential function, we're going to write this as a product. Because xi's are independent, so are e raised to the power t times xi squared. Because they are independent, we can pull out this product. Remember, the expectation of the product of independent random variables is equal to the product of the expectations of those random variables. And now, because those xi's have identical distribution, we're going to simply write this product as a power. The case power of the first term, because the distribution are the same and thus the expectations are the same. And now this question boils down to the computation of just the expectation of e to the t x1 squared. Now the problem boils down to the computation of the expectation of e to the power t times x1 squared. Here, recall that x1 has standard normal distribution, and this part is a continuous function of x1. So we can use the so-called the law of the unconscious statistician. This is a very famous tool to compute the expectation of a continuous function of a random variable whose density function is known. But the law of the unconscious statistician, this expectation is equal to the integral. This looks like the integral of the density function with an additional term which plays the role of this continuous function. Here, this little x is just a real variable. I recall that this part, the underlying part, is the probability density function of a standard normal distribution. If you don't remember this, the law of the unconscious statistician, you can look at the Wikipedia page. But I believe this is a very common fact in the probability theory, which should be covered in the basic probability class. So let's continue with this. We'll first simplify it. Now let's first combine the coefficients. From here, we observe that this integral is finite if and only if t is less than 1/2. And to compute this, we're going to make a substitution. And it follows that this integral will be transformed into this. This is basic calculus. And now if you pull out this 1 over square root of 1 minus 2t, the rest will be precisely equal to 1. Why? If you're lazy, you can just say because this guy is the probability density function of the standard normal distribution. So if you integrate over the whole real line, you get 1, the probability of the whole space. But you should also know this can be computed by many ways. The most famous trick is that you can transform this into a double integral, which should be covered in your calculus 3. So anyway, we have computed the moment generating function of a random variable that follows a chi-square distribution of k degrees, with k degrees of freedom. So the moment generating function here will be the case power of this. Whenever t is less than 1/2. When t is greater or equal to 1/2, this integral will become infinite. So this is our computation result.